So now we are going to discuss about dinitrogen, its preparation, properties and uses. So we are starting with its preparation. Okay, there are different methods for the preparation of this dinitrogen. 1 minute. Yes, dinitrogen. So commercially means the large scale production of this dinitrogen. It is by the liquefaction and fractional distillation of air. Okay, dinitrogen, it is prepared by the liquefaction and distillation of air. That's the method of preparation in large scale method. Okay, large scale production of nitrogen, it is through the liquefaction and fractional distillation of air. Because the atmospheric air, it contains mixture of gases, right? So by liquefying and through the fractional distillation, you know the difference between distillation and fractional distillation. In the case of fractional distillation, if the difference in the boiling point is less than 25 Kelvin, we will use this fractional distillation. Okay, so this atmosphere, it contains a mixture of gases. By the liquefaction and fractional distillation of air, this dinitrogen will be obtained. Then the second one, the laboratory preparation. Okay, laboratory preparation method. Here you can see ammonium chloride and sodium nitrate. Ammonium chloride and sodium nitrate combined together, and this nitrogen, then water, and sodium chloride is formed. So this is the method of preparation in laboratory. In this method, along with this nitrogen, water, and sodium chloride, some amount of NO and HNO3 also formed. Okay, NO and HNO3 formed along with these products, nitrogen, water, and sodium chloride. And we will remove these impurities by passing these two gases through aqueous sulfuric acid. To remove these two impurities, NO and HNO3, we will pass these two mixtures or gases through sulfuric acid containing potassium dichromate. That is H2SO4. It will pass through H2SO4 and potassium dichromate, K2Cr2O7. Clear, children? So this is the laboratory method of preparation of dinitrogen. Along with nitrogen, water, and sodium chloride, small amount of NO and HNO3 will be formed. This is considered as impurities in the preparation of this dinitrogen. So it will be removed from this product by passing it through H2SO4, sulfuric acid and potassium dichromate. That's the method. So this is the second method for the preparation of nitrogen. Then the third method, that is thermal decomposition of this ammonium dichromate. Okay, thermal decomposition of ammonium dichromate. NH4 twice Cr2O7, that is ammonium dichromate. Here it is thermal decomposition. Thermal decomposition means on passing heat through the solution, it will be decomposed. Here also nitrogen, water, and chromium oxide will be obtained. The desired product is nitrogen. So this is another method for the preparation of nitrogen. First one is the large scale production. Second one, laboratory method. Third one also belongs to laboratory method. Okay. Then the fourth one, that is for the formation of very pure form of nitrogen. Very pure form of nitrogen. And here the method is that for obtaining by thermal decomposition of sodium or barium azide. Okay, here also the same process, thermal decomposition. So on passing heat to this sodium or barium azide, barium and nitrogen molecule will be obtained. So these are the different methods of preparation of nitrogen molecule. First one, that belongs to large scale production. Second and third, lab preparation or laboratory preparation methods. Then fourth one, to obtain the very pure form of nitrogen. We are using this method. Clear, children? All of you, please switch on your videos. This is clear for you?
Yes, ma'am.
Okay. Then we are moving to the properties of dinitrogen. Properties of dinitrogen. So in the case of properties of dinitrogen, you know that dinitrogen is a colorless, odorless, tasteless, and non-toxic gas, right? Colorless, it has no color, then no smell, that is odorless, then tasteless, non-toxic gas, non-toxic gas, and it has two stable isotopes. You know that isotopes, they are the elements with same atomic number but different mass number, right? We can obtain different forms of isotope from nature itself. So the two stable isotopes of nitrogen, nitrogen 14 and nitrogen 15. Okay, with their mass number 14 and 15, atomic number remains same, 7 itself. So these are the two stable isotopes of nitrogen, and it has a very low solubility in water. It has a very low solubility in water, and it is quite inert at room temperature. What's the meaning of inert? They will not highly reactive. The reason is that high bond enthalpy of nitrogen-nitrogen triple bond. In the case of this dinitrogen, you know that triple bond exists between two nitrogen atoms, right? Due to this triple bond, it is quite inert at room temperature. It does not involved in certain chemical reactions. At room temperature, it will remain inert. It do not take part in chemical reaction. On heating, it will react with other substances to form products. So the reason is that high bond enthalpy. High bond enthalpy means high energy is required to break that triple bond between two nitrogen atoms. Clear, children? Always this bond enthalpy means the energy required to break the bond between two atoms. In the case of multiple bonds, including double bond and triple bond, it will be higher compared to that of single bond. Clear? Is clear? Yes, it is quite inert at room temperature because of high bond enthalpy of nitrogen-nitrogen triple bond. Then as temperature increases, the reactivity increases. At room temperature, it will not react. But when we increase the temperature or during heating, it will be react with other elements to form compounds. That means their reactivity increases. Okay. Then at higher temperature, this nitrogen atoms, they will react with both metals and non-metals. At higher temperature, this dinitrogen, it will react with both metals and non-metals. These two reactions that belongs to the reaction of nitrogen with metals. Nitrogen with metals. Here you can see lithium. That's an example for metal. Lithium will react with nitrogen to form lithium nitride, right? Lithium nitrate. So this nitrogen or dinitrogen molecule, it will react with metals to form ionic nitrates. Ionic nitrates. Ionic nitrates. Examples are lithium nitrate, then magnesium nitrate. Okay, clear, children? Metal plus N2. Metal plus dinitrogen will give ionic nitrates. Examples are lithium nitrate, magnesium nitrate. Then in the case of non-metal, okay, non-metal, it will give covalent nitrates. Non-metal react with nitrogen to form covalent nitrates. That means the bonding is covalent bonding. That's why it's known as covalent nitrates. In the previous case, it will be ionic bonding. Okay. Metals react with nitrogen molecule to form ionic nitrates. That means ionic bonding exists between the molecule. And here non-metals react with nitrogen molecule to form covalent nitrates. That means covalent bonding exists between the molecules. Okay. Then one important chemical reaction that happens between nitrogen and hydrogen, that's the formation of ammonia. that is known as Haber's process. Industrial preparation of ammonia, that's by Haber's process. Nitrogen and hydrogen molecule combines together to form ammonia. Here the temperature is maintained at 773 Kelvin at higher temperature. Always this dinitrogen, it will be inert at room temperature, and on increasing this temperature, their chemical reactivity increases and they will react with other atoms or molecules to form compounds. Okay, so at 773 Kelvin, this nitrogen will react with hydrogen to form ammonia. This process is known as Haber's process. Okay, Haber's process. Clear, children? Meenakshi, Nandana, Anna, Naurin, Evelyn, Rijaz, Sharon, Adul, all of you, please switch on your videos. Nandana, can you please read the points about the properties?
Properties, it has two stable isotopes, N14 and N15. It has a very low solubility in water.
Yes.
It is quite inert at room temperature because of high bond enthalpy of nitrogen triple bond. As temperature increases, reactivity increases. It shows the following reactions. 6 lithium plus N2 gives 2 lithium nitride molecules. 3 Mg plus N2 gives Mg3N2. N2 plus 3H2 gives 2 NH2. Haber's process.
Okay. Shall I move to next slide, children? Okay, I think next one, ammonia. Before that, we have to discuss about the uses of nitrogen. Okay, uses of dinitrogen. And who will read that? Yes.
Like in the properties, you mentioned about the freezing point and boiling point. That's also important.
Yeah, low freezing and boiling point. Yes, yes. Can you read, Adul, the uses of dinitrogen?
The main use of dinitrogen is in the manufacture of ammonia and other industrial chemicals containing nitrogen. Example, calcium cyanamide.
Yeah.
It also finds uses where an inert atmosphere is required. Example, in iron and steel industry, inert diluent for reactive chemicals. Liquid dinitrogen is used as refrigerant to preserve biological materials, food items, and in cryosurgery.
Okay, so there are mainly important 3 uses. First one in the manufacture of ammonia, Haber's process. Okay, then the second one, that's about whenever the inert atmosphere is required. Okay, in some chemical reactions, inert atmosphere is required, and we will provide this nitrogen, because in the case of nitrogen, we have learned that at room temperature, it will not take part in any chemical reaction. Only at higher temperature, it was involved in certain chemical reactions. So whenever inert atmosphere needed, we will provide this nitrogen. Then it will also use as a refrigerant to preserve biological materials, food items, and in cryosurgery. I didn't search for this cryosurgery. I will inform it in the next class. Okay. Yes. Then next we are moving to ammonia. Okay. Here also same thing, preparation, properties, uses. Preparation, properties, uses. So now we are starting with preparation. So in the case of ammonia, its chemical formula is NH3, right? We already learned one process for the manufacture of ammonia. What was that? What's the name of the process for the production of ammonia in large scale? Haber's process. Okay. Along with that, there are certain other methods. The first one, that's about, ammonia, it's present in small quantities in air and soil, where it is formed by the decay of nitrogenous matter. Okay, from the decay of nitrogenous matter, small amount of ammonia will be produced in air and soil already. Then this first method of preparation, that's from urea. Okay, urea. This NH2, CONH2, that's the chemical formula of urea. NH2CO, NH2. It will react with water molecule to form NH4 twice CO3, ammonium carbonate. Then it will be converted to this ammonia, then water molecule and carbon dioxide. Here this reaction is a reversible reaction. Last one. So there is a chance for this ammonia and water molecule, then carbon dioxide again to form ammonium carbonate. Clear, children? First, urea will react with water molecule to form ammonium carbonate. Then this ammonium carbonate dissociate into ammonia, water molecule, carbon dioxide. In the second reaction, that's a reversible reaction. So there will be chances for this ammonia, water molecule and carbon dioxide combined together to form this ammonium carbonate. Clear? That's the first method of preparation from urea. And chemical formula of urea, that is NH2CO, NH2. NH2CO, NH2. Simple method. Just dissolving in water to form ammonium carbonate, then it dissociate to form ammonia, carbon dioxide and water molecule. Okay. Then another one, that's a small scale production of ammonia. Okay. It's obtained from ammonium salts. Ammonium salts. The first method, you can see that ammonium chloride. This ammonium chloride, ammonium sulfate, both are ammonium salts. So first one, ammonium chloride, it will react with calcium hydroxide to form ammonia, water molecule, then calcium chloride. The required product is ammonia. So from ammonium salts also, ammonia can be produced. Ammonium salts. Ammonium salts. First one, ammonium chloride. Second one, ammonium sulfate. Ammonium sulfate will react with sodium hydroxide to form ammonia, water molecule, then sodium sulfate. This is another method of preparation of ammonia. Only small amount of ammonia can be produced using this method. Large scale production, that's mainly based on Haber's process. Okay. So this is the main important one is that's about Haber's process. Haber's process. Here nitrogen and hydrogen reacts together to form ammonia. Nitrogen and hydrogen, it will react together to form ammonia. Clear, children? So first one, it's a laboratory preparation from urea. It will dissolve in water to form ammonium carbonate. It will be decomposed to ammonia, water molecule, carbon dioxide. Then the second method, small scale production from ammonium salts. Both type of salt here, ammonium chloride and ammonium sulfate. From both salts, we can prepare ammonia by reacting with other salts. Then the third one, large scale method, that's very important, Haber's process. Clear? Clear, children? Okay. Yes, then we are moving to the Haber's process. Okay. Some essential conditions are required for this Haber's process to occur. So what are the conditions in accordance to Le Chatelier's principle for the formation of ammonia? You have learned that in the case of reversible reactions, there are certain conditions required, right, to increase the rate of forward reaction. Because in reversible reaction, chances for the forward reaction and backward reaction remains the same. So in order to obtain more product, we will always favor for forward reaction. And there are certain factors that will help in the increasing the rate of formation of product. So here, these three are the important conditions for this Haber's process to occur. First one, pressure of about 200 atm. Okay, pressure should be near to 200 atm. Clear, children? Then the temperature of about 700 Kelvin. Pressure of about 200 atm and the temperature 700 Kelvin. Then the catalyst used here, iron oxide with small amount of potassium oxide and aluminium oxide. Clear? The catalyst used here, iron oxide with small amount of potassium oxide and aluminium oxide. So these three are the essential conditions according to Le Chartier's principle for the formation of ammonia. Pressure of about 200 atm, temperature of about 700 Kelvin, then catalyst used is iron oxide with small amount of potassium oxide and aluminium oxide to increase the rate of attainment of equilibrium. And the earlier times we will use catalyst iron with molybdenum as promoter. Okay, iron with molybdenum as promoter. Iron as catalyst, then molybdenum as promoter. What's the role of promoter? It will increases the activity of catalyst, right? We have learned it in the chapter surface chemistry, right? I think so. Yeah, so iron as catalyst and molybdenum as promoter in earlier days, but nowadays we are using iron oxide with small amounts of potassium oxide and aluminium oxide. And this is the flow chart to explain this Haber's process. Okay, this is the flow chart. Same thing in your textbook also, page number 176. So here, you know, the reagents are hydrogen and nitrogen, right? Both this hydrogen and nitrogen, they are gases. They will pass to the compressor. What's the role of compressor? It will apply high pressure and converted it into the form of liquid. Okay, it will compress. Clear, children? Then from this compressor, it will be passed to catalyst, that is iron oxide with aluminium oxide and K2O at 700 Kelvin. The high temperature should be maintained. And in this compressor, the pressure should be 200 atm. Then when they are passing through this catalyst, this nitrogen and hydrogen, it will react to form ammonia. And it can be available in the form of liquid ammonia. And I told you this is an reversible reaction. And there will be chances for this ammonia to dissociate again into nitrogen and hydrogen. And when small amount of nitrogen and hydrogen will be escaped from this ammonia, it will be again passed through this catalyst iron oxide and more amount of ammonia will be obtained. Clear? This nitrogen and hydrogen gases, they will pass through the compressor. There will be apply high pressure of about 200 atm. Then it will be passed through the container containing catalyst iron oxide with aluminium oxide and K2O at 700 Kelvin. This nitrogen and hydrogen reacts together to form ammonia. That's in the liquid form. That is, liquid ammonia will be obtained. And a small amount of hydrogen and nitrogen will be dissociated from this ammonia. It will be again back to this process using a certain pump. So that's about the process of production of ammonia, Haber's process. Yeah, sure.
What is this pump?
That's to convert this nitrogen and hydrogen again to this one. There is no such other purpose for this pump. I think so. Okay, I will check and tell you if there is any role there. So that's about the method of Haber's process. Simple one, right? Nitrogen and hydrogen passes to compressor, then high pressure applied. It will be passed to the catalyst, iron oxide, aluminium oxide and potassium oxide. Then it will be converted to ammonia. If any amount of gas will be escaped from this ammonia, it again back to this process. That's it. Is this clear? Yes. Then we are moving to the properties. Properties of ammonia. So this ammonia is a colorless gas with a pungent smell. Colorless gas with pungent smell. What is pungent smell? We can't tolerate that. Okay, I think during this laboratory experiments, there is some techniques to identify the salt using the smell. So first we will add some chemical and smell the solution to identify whether ammonia is present there or not. Okay, there is one category of experiment to find out the cation and anion. In this section, the method of finding out this ammonia by smelling this odor. That's it. So it's a colorless gas with pungent odor. And the structure of ammonia, it has a pyramidal structure with one lone pair of electrons. Here you can see the structure of ammonia. It's a pyramidal structure and one lone pair of electrons remains in nitrogen. Because the 3 electron pairs are shared between this hydrogen, then 2 lone pairs that do not involve in chemical bonding. That remains as lone pair of electrons. And the hybridization present is sp3 because single bond is there, right? In the case of NH3 molecule, single bond is there, so it is sp3. But the tetrahedral angle gets reduced to 107.8 degree because of the repulsion of lone pair of electrons. Here, the tetrahedral angle is reduced to 107.8 degree because of the repulsion of lone pair of electrons present on nitrogen atom. It's reduced from the actual tetrahedral angle and its hybridization is sp3 hybridization. And this ammonia gas, it's highly soluble in water and its aqueous solution is weakly basic due to the formation of OH minus ions. This ammonia gas is highly soluble in water and its aqueous solution. Aqueous solution means ammonia reacts with water, ammonium hydroxide will be formed, right? It's weakly basic. We have learned this different types of acids and bases, right? Strong acid, weak acid, strong bases, weak bases. Among that, this ammonium hydroxide that belongs to a weak base. That's due to the formation of OH minus ions. So this NH3, it will react with H2O molecule to form ammonium hydroxide. That's splitted here. That's why it is NH4 plus OH minus. Clear? Ammonium gas is highly soluble in water. That means NH3, it will react with H2O to form NH4OH. That's the compound. But here it is splitted as ions, NH4 plus OH minus. That's the difference. And the basic nature, it is due to the presence of this OH minus ions. But it is not a strong base, it's a weak base. It's a weak base. Then in water, ammonia forms hydroxide, which is known as ammonium hydroxide. That is NH4OH. NH4OH. Clear, children? Then their freezing point and boiling point also given here in textbook. Its freezing point is 198.4 and boiling point 239.7. Clear? Yes. Then about the chemical reactions. Okay, chemical reactions. So here first one, what happens when ammonium hydroxide is made to react with zinc sulfate and ferric chloride? Here you can see the two chemical reactions. Ammonium hydroxide react with zinc sulfate and ferric chloride. First one, ammonium hydroxide with zinc sulfate. Here you can see displacement reaction occurs. Okay, displacement reaction occurs. This anions of both these salts, it will be exchanged between these compounds. That means zinc hydroxide and ammonium sulfate will be produced. And the zinc hydroxide, that's in the form of a white precipitate. You know that in the case of double displacement reactions, it's also known as precipitation reaction, right? A precipitate will be formed in all double displacement reaction. Here, it's an example for double displacement reaction because the both anions are exchanged between these two salts. You can see zinc sulfate converted to zinc hydroxide. Ammonium hydroxide is converted to ammonium sulfate. So it's an example for double displacement reaction. It is also known as precipitation reaction. There will be a precipitate formed during this reaction. The second one also same. Yes. Here this ferric chloride, it will be reacted with ammonium hydroxide. Okay. Ferric chloride react with ammonium hydroxide and here ferric oxide and ammonium chloride will be produced. This ferric chloride, that's a brown colored precipitate formed. Brown colored precipitate formed. Clear, children? That's about the reaction between ammonium hydroxide with zinc sulfate and ferric chloride. Then the next one, how are the metal ions like copper and silver detected using ammonia? How are the metal ions like copper and silver can be detected using ammonia? When this copper, that's in blue color, right? Copper sulfate solution, that's blue colored. This copper Cu2 plus, here also it's in the form of ion, that's from certain salt, copper sulfate, like that. So it's blue colored solution. When it will react with this ammonia, it will be converted to deep blue. So to detect if copper ions are present in that solution, we can add certain amount of ammonia to that solution. If deep blue colored precipitate will be formed, we can confirm that copper is present in that solution. Clear, children? If some blue colored solution given to you, and the question is that to identify the copper ions present or absent in that solution, you can add small amount of ammonia into that solution, and if deep blue colored will be obtained, you can confirm that copper is present in that solution. The same way in the case of silver. Silver also react with chlorine molecule, chlorine ion to form AgCl. Okay, then a white precipitate will be obtained. Then this AgCl again react with ammonia. When a colorless solution is obtained, we can confirm that silver ion is present in that solution. Clear, children? Silver, that's a colorless solution. Colorless solution will be reacted with chlorine to form white colored precipitate, that is AgCl, silver chloride. Then the silver chloride reacts with ammonia. Again, it will become colorless. Then we can confirm that silver ion is present in that solution. So this is the method of identification of copper and silver using ammonia. The first case, when we add ammonia, it will be converted to deep blue. And in the second one, colorless solution will be converted to a white precipitate. Then again, it becomes colorless. Okay. Clear, children? So it's also important. From the reaction, what typical characteristics of ammonia can we gather? So the presence of lone pair of electrons on the nitrogen atom of the ammonium molecule makes it as a Lewis base. So here ammonia, you can see that lone pair present on nitrogen atom. This lone pair present on nitrogen atom will make this ammonium molecule as a Lewis base. It will donate electron pair and forms linkage with metal ions, and this finds an application in the detection of metal ions. Here we are using this ammonia to identify copper and silver ions present in that solution. Here we are using the property of nitrogen atom. It will be some lone pair present in that nitrogen atom. So it will act as a Lewis base. Lewis base means that will donate electron pair and forms linkage with metal ions. That's why certain amount of precipitate will be formed, and we can confirm the presence of copper and silver ions. Clear, children? Any doubt? Yes or no?
No.
No, okay. Then now we can discuss the uses of this. Yeah. Yeah, sure.
Can you show the previous slide?
Sure. This one, right? This one?
Only the third point can you explain now?
Yes, ammonia forms hydroxide, which is known as ammonium hydroxide. That means here it is in the form of ions, right? NH4 plus OH minus. They will combine together to form NH4OH, ammonium hydroxide. You can split it into ions, NH4 plus OH minus. When they combine together, it will become ammonium hydroxide. Okay. Yeah, then before moving to nitric acid, what about the uses of ammonia? Children, switch on your videos. Gayatri, can you please read the uses?
Ammonia is used to produce various nitrogenous fertilizers, ammonium nitrate, urea, ammonium phosphate, and ammonium sulfate, and in the manufacture of many inorganic nitrogen compounds.
Yes.
The most important one being nitric acid. Liquid ammonia is also used as a refrigerant.
So these are the common uses. Ammonia is the main content in all fertilizers, right? So it is used to produce various nitrogenous fertilizers. That means it will provide nitrogen for plants through the fertilizers. Then it is used in the manufacture of some inorganic or nitrogen compounds, nitric acid. So this nitric acid is from this ammonia. You have learned that from dinitrogen we will prepare ammonia. Then from ammonia we will prepare nitric acid. Okay. Then this liquid ammonia, it is also used as a refrigerant. So these are the important uses of ammonia. Then this part, oxides of nitrogen, that's not included in the syllabus. So you can skip this part. The next one is nitric acid. That's the third main compound from nitrogen. So again, we are moving to the preparation method, then properties, then uses. So nitric acid, the preparation of nitric acid. In the laboratory, nitric acid is prepared by heating potassium nitrate or sodium nitrate and concentrated H2SO4 in a glass retort. So this sodium nitrate or potassium nitrate, it will react with sulfuric acid H2SO4 to form sodium hydrogen sulfate and nitric acid. Okay, this is the laboratory method of preparation of nitric acid. Potassium nitrate or sodium nitrate, it will react with H2SO4 to form this nitric acid. And the large scale production of this nitric acid, it is known as Ostwald's process. Okay, Ostwald process. In the case of ammonia, the process is known as Haber's process. Here it is known as Ostwald's process. Okay, in this Ostwald process, I told you from this ammonia we can prepare nitric acid. So here the starting material is ammonia. It will react with oxygen to form nitric oxide. Just wait, children. I think I skipped one step. Yes, nitric oxide and water molecule will be formed. This is the first step. Okay, nitric oxide and water molecule will be produced. Then the second step, this nitric oxide that will react with again oxygen. That means oxidation take place and it will be converted to NO2, nitrogen dioxide, to NO2. This is the second step. Ammonia, it will react with oxygen to form nitric oxide. Then nitric oxide again oxidizes to form nitrogen dioxide. Then the third step, nitrogen dioxide reacts with water molecule to form nitric acid. Clear? Then here you can see in the third step, a small amount of nitric oxide again produced, right? NO. Along with HNO3, you can see NO. This will be again used for the second step. Clear? Here in the third step, along with nitric acid, NO is produced, that is nitric oxide. This nitric oxide again used for second step for the production of nitrogen dioxide. So the maximum yield will be obtained. Clear? This is clear, children?
Yes.
Yes. So there are mainly three steps for the large scale production of nitric acid through Ostwald process. Starting from ammonia, it will react with oxygen to form nitric oxide. This nitric oxide reacts with water molecule to form nitric oxide reacts with oxygen to form nitrogen dioxide. Then nitrogen dioxide reacts with water molecule to form nitric acid and nitric oxide. This nitric oxide again goes to second step for the formation of nitrogen dioxide. So the large scale production of this nitric acid, it is known as Ostwald process. In the case of ammonia, it is known as Haber's process. Clear about the preparation methods? Yes. Then here the nitric acid will be obtained. It will be concentrated by distillation to obtain the pure form of nitric acid. And here this one is the structure of nitric acid. OH, then NO2 group, HNO3, right? HNO3. This is the structure. And this type of structure is known as planar structure. Planar structure. So next we are moving to the properties. Properties. In the gaseous state, it exists as a planar molecule. In gaseous state, it exists as a planar molecule and it behaves as a strong acid giving hydronium and nitrate ions. Always the acids that will donate H plus ions, right? Here this nitric acid is an example for a strong acid. So it will give H plus ions. But along with water molecule, it will be H3O plus, that is known as hydronium ion. From this nitric acid, it will donate H plus ion. This H plus ion react with water molecule to form H3O plus hydronium ion. So that's the second reaction. HNO3, it will react with water molecule to form H3O plus and NO3 minus. And then we can discuss the remaining things in the next class. Now it's time, right? Yes. So we have discussed about dinitrogen, its preparation methods, properties, uses. Okay. The next one is ammonia, its preparation method, properties, uses. And the third one is nitric acid. We have completed the preparation methods. Then we have started the properties. Then properties and uses we can complete it in the next class. Then in the case of this phosphorus, it's deleted. Phosphorus, phosphine, then phosphorus halides, oxoacids of phosphorus. These all portions are deleted. So after the completion of nitric acid, we will move to group 16 elements. Okay.
But
Yeah.
the structure also, can you show me?
Which one? Structure of nitric acid. Yeah, I will show it in the next class. Okay. Okay, children. Then now it's time. So I'm winding up the session. Thank you, children. Bye. See you in the next class. Yes.